In this video, we're going to talk about Hess's Law. Consider this. You want to climb Mount Kilimanjaro. One route is to go straight up. Another route is to do a long, twisty, windy route to get there. In chemistry, we use the term state function to refer to a property of a system that depends only on its current conditions, not on its history. So whether you take the straight route up Mount Kilimanjaro or the windy one, you end up at the same spot. And chemistry doesn't care how you got there. Enthalpy changes of reactions are state functions. We don't care how you get there. According to Hess's law, you can add together delta H from lots of different steps of a reaction, a long multi-step reaction, to get the overall enthalpy change. And it doesn't matter whether you break it up into 2 steps or 3 steps or 4 steps. Consider this. You've got A becoming D, and one way to get there is reaction 1 that goes directly. But you could also get there by going A to B, B to C, and C to D. And let's say if you, the chemist, can more easily conduct those 3 smaller reactions much easier than the direct one, you could simply add together the delta H values of the 3 smaller reactions and arrive at the delta H for the direct reaction. If a reaction can take place by more than one route, then the total enthalpy change is the same regardless of the route taken. And a lot of times in chemistry, maybe I can't make A go directly to D. Perhaps it's physically impossible. Perhaps it requires temperatures and pressures that I couldn't achieve in lab. But I can make A go to B and B go to C and C go to D, and more indirectly get that A to D measurement of enthalpy change. When we consider Hess's law problems, we're adding together chemical equations. And we get to add together chemical equations the same way that you add together equations in math class. Consider this one. Your overall equation is carbon plus oxygen yields CO2. We don't know the delta H. But we do know 2 steps that can add up to that overall equation. Carbon plus, don't worry about a fractional coefficient. It'll still work out just fine. Half of a mole of oxygen yields CO. We've got a delta H value of negative 110.5. And then in step 2 of the reaction, carbon monoxide plus half of a mole of oxygen yields carbon dioxide. We get a delta H of negative 283 kilojoules. If we were to add these 2 equations together, notice that the 2 half moles of oxygen adds up to 1. The carbon and the carbon monoxide from the reactant sides add together, so those appear once more. On the product side of the equation, carbon monoxide and carbon dioxide are written to the right of the arrow. If you have CO, carbon monoxide, on opposite sides of the arrow, it's as if they subtract. They can cancel out. So what we're left with, after canceling out the carbon monoxide, is carbon plus 1 mole of oxygen yields CO2. That's our overall equation. That was the equation whose delta H value we wanted to get. So if we've got a delta H for step 1 and a delta H for step 2, and those 2 steps add together to the overall equation, then the sum of delta H1 and delta H2 should be the overall delta H. And it is. If you add together negative 110.5 and negative 283, you get the overall delta H of negative 393.5. The sum of the enthalpies of the individual steps add up to the enthalpy of the overall reaction. We're going to tackle problems like this, but the difference will be sometimes we have to multiply the coefficients in a reaction. Sometimes we'll need to make the reaction flip around, make products reactants and make reactants products. To tackle that, I want you to have these steps in your notes. First, identify a substance that only appears once among the reaction steps. The easiest way to do that is to scan. So you look at the overall equation, you look at the reaction steps that are proposed to get to the overall equation, and you try to find something that only appears in one place. Ask yourself, where does within the reaction steps, where does that substance appear? Is it on the left side of the equation or the right side of the equation? And what is its coefficient? Compare that position and coefficient to where it's found in the overall equation. And then ask yourself, what needs to happen in order to get that substance in the proper position and with the proper coefficient? What do we need to do to the reaction step, if anything? It might be nothing, to make sure that you're adding up to the overall equation. Sometimes, to get the reaction steps to add up to the overall reaction, you might need to reverse the equations around. If you do that, that means you're going to make reactants products and products reactants. If that's the case, the sign of delta H would change. So if it was a negative delta H to begin with, it will become positive. If it's positive to begin with, it becomes negative. Sometimes you'll need to multiply coefficients. If you do that, your delta H needs to multiply as well. So if you double all the coefficients, you've got to double the delta H value. Let's try a couple of sample problems because sometimes these steps are a little hard to visualize. We're going to go over to our Jamboard here. Here's our problem. Determine the overall enthalpy change for this equation. 2 sulfurs plus 3 oxygens yields 2 sulfur trioxides. Given these 2 reaction steps, and the delta H values for each step is given. What I'm going to do first is scan. I want to look among these reaction steps and try to find a substance that only appears once. I would not want to pick oxygen. Oxygen appears in step 1 and it appears in step 2. So I'm not going to pick that one to try to figure out what to flip or not flip. Also, I'm not going to pick SO2. SO2 appears in both step 1 and step 2. But sulfur itself is fine. So would sulfur trioxide be a fine thing to look at. So let's start with the sulfur. I see that in step 1 of the reaction mechanism, that is the series of steps that adds up to the overall equation, it has a coefficient of 1 and it appears on the left side of the arrow. In the overall equation, it's also on the left side of the arrow, but it has a coefficient of 2. So then I'm thinking to myself, what do I need to do to sulfur in step 1 to make it look like the sulfur in the overall equation? I'm not going to change the equation, reverse the equation. I'm going to keep it in this order, but I do want to double the coefficients. So our strategy is to double step 1. Before we move on, I want you to look at the other, what I'm calling the anchor substance. In step 2, SO3 appears on the right side of the arrow and it has a coefficient of 2. In the overall equation, it also appears on the right side of the arrow and with a coefficient of 2. That's perfect. You don't need to do anything to that reaction step to make SO3 go to the right spot. So we're going to keep step 2 exactly as is. Keep step 2, but double step 1. Okay. If we do that, if we double step 1, we'll end up with 2 S's plus 2 oxygens yields 2 SO2. I'm simply rewriting step 1, having doubled all of the coefficients. So instead of 1 S, I'm writing 2 S's. Instead of 1 O2 molecule, I'm writing 2. Instead of 1 SO2, I'm writing 2. The delta H of that manipulated step 1 would be twice, 2 times, negative 296. So that's negative 582. So we have to double the value of delta H if you double the coefficients. Now let's add, we're going to simply rewrite step 2 exactly as is. You don't need to change anything because our strategy was to keep step 2. So this one's simply a rewrite-o. And then we're going to add the two equations together, just like in math class. If you can cross something out, so I noticed that 2SO2 appears on the right side in step 1, and 2SO2 appears on the left side in step 2. Their coefficients match, and they're the same substance. Those cross out. What we're left with, 2S. Notice that you've got, in step 1, 2 oxygens on the left side, and in step 2, 1 oxygen on the left side. Those will add together to give you 3 O2 molecules. And then lastly, we have 2 SO3 molecules on the right side. Did we reproduce the overall equation? Does what's written here match what's written here? Yes, we've done it. So now, this is the easy part. After doing the manipulation of the reaction steps, you agree that you've found the overall equation, then all you need to do is add the numbers, the delta H's together. So negative 582 plus a negative 198.2 gives you negative 790.2. And we'll keep the unit kilojoules. The hard part is figuring out what to manipulate, what step to flip around and what not to. Let's try one more. Our overall equation is listed at the top. 2CO plus 2NO yields 2CO2 and N2. Let's scan the reaction steps and try to find something that appears uniquely. So like in step 1, I see that CO appears only in step 1. It's now nowhere in step 2. I see that 2NO appears only in step 2. It's nowhere in step 1. The only thing that wouldn't be a good choice in this case is the O2, because that appears in both equations. If in step 1 we pick the anchor or the substance to look at of CO, I notice that it's on the left side of the equation in step 1, and it has a coefficient of 2, and that matches its position and coefficient in the overall equation. Therefore, we should keep step 1. Don't change anything about step 1. In step 2, I see that NO appears on the right side and it has a coefficient of 2. In the overall equation, I'm finding NO. It's on the left side of the equation. It has a coefficient of 2. So this time the coefficient's in great shape. It's exactly what appears in the overall equation. But we do need to flip the equation around. We've got to make reactants products and products reactants. First, I'm going to rewrite step 1 exactly as it appears, no changing. Keep the delta H value exactly as it was, negative 566. But step 2, I'm going to rewrite it, having flipped it around. I'm going to put the 2NO on the reactant side, and I'm going to put the N2 and the O2 on the product side. Having done that, our delta H becomes, if it was originally positive 181, now we've got to flip the sign of the delta H to make it negative. If we've done this right, we should be able to add these two equations together and produce the overall equation. Notice that in step one, O2 appears on the left side and with a coefficient of 1. And after having flipped equation 2, O2 appears on the right side with a coefficient of 1. Now I'm simply going to rewrite what we have. 2CO and 2NO on the left side. And on the right side, we've got 2CO2 and N2. Did we reproduce the overall equation? Is what we have up at the top the same as the sum of the two reaction steps? Yes. And by the way, it wouldn't matter if you had written, like if I wrote N2 plus 2CO2, the order in which you write the substances doesn't matter as long as you've got the right things in the right places. Okay, so if you're confident that you've added the equations together properly to get the overall equation, then we simply got to add the two delta H values together. So negative 566 plus a negative 181 gives a negative 747 kilojoules for the unit. All right, students, good luck. Some of the homework is going to have you try problems where you even need to flip and double or flip and times by half the coefficients. You can do both things to a reaction step. It's possible to both flip it around and change the coefficient. Give it a try. Thanks for your good work.